Hi, thank you for joining our next session. Mal Tuvek, how NLP can help us understand web attackers. I'll start with some motivation. Ori and I are from Imperva. Among other things, we are WASP providers. So what we have in the security research team, we are seeing a lot of malicious web traffic that is coming to our customers. And it comes in different types of attacks. We see a significant amount of data there. And all the time we're trying to continue and improving our security models, our attack models, understand better what attackers are trying to do and how attacks look like, and therefore to provide better and better solutions. So what we did here, we tried to build a new security model, a new glasses to look on malicious web traffic. And with this better attack modeling, we try to use it for different applications like analytics of attacks, reconstruction of the attack narratives to understand how the attack looked like and what are the attackers want to achieve. And also for improving the accuracy of the rules that we are using and to detect false negatives. I'm ITSIK MANTIN. I'm a lead scientist at Imperva. I'm a security innovator, algorithm developer, and in general, a problem solver. In the last couple of years, my main focus is to harness the huge leap in AI technology that change essentially every industry, to use it and to harness it for the sake of improving cybersecurity applications. I hate to be at the office, so I compensate my office hours with a lot of hiking, biking, trail running, and anything that you can do outdoors.
And I'm Ori. I'm a data scientist at Imperva, and I work alongside ITSIK. I like to find innovative solutions to complex problems, and I'm very disappointed with the last season of Game of Thrones. Yeah, okay.
Okay, so I think every security vendor, regardless whether it is web or database or antivirus, everybody's using AI. It is being used for many different usages. I think they can essentially be divided into four. There is this usage of AI for automation of processes, like incident response. Also for enhanced attack detection, like next generation antiviruses. And they're also being used for security modeling and attack analytics. And essentially our research focuses on belongs to the last two, security modeling and to attack analytics. So I'll start, our research uses actually the data categorization of malicious web traffic to different attacks. So the most popular attacks in our customers and probably in every website are cross-site scripting, SQL injection, remote command execution, and malicious file upload, and path traversal. The data that we're using for this research is again comes from our couple of hundred of thousands of websites protected by our cloud WAF, aka Encapsula, and we are monitoring, seeing about 200 million, probably sometimes more, sometimes less, data points every day. Each one of them represents suspicious activity that was detected in web requests that arrived to one of our customers. Now, something a little delicate here. So we have many sites that we are monitoring and seeing and protecting. Now, our purpose within this research is to understand the attacks and to model the attacks. However, in some sense, like in quantum theory, the fact that we are protecting the website and we are stopping attacks, it has an impact on the attack itself. Because if the attacker wanted to do A, B, C, D, E, then he will probably do A, B and get blocked, and then will not make the C, D, E. However, we have a significant amount of customers that are working in alert-only mode. So we focus the research on data that came from them. And in that sense, we get this benefit of looking at attacks from the beginning till the end, without impacting by our analysis or our presence the progress of the attack. And the model itself, we're using a model that is called the word-to-vec. How many here in the audience heard about the word-to-vec? Okay, so I'll provide some more details. So as most of you know, some of the leaps forward that are attributed to AI are in the NLP, speech recognition, translation of text, and some of these, significant part of this, can be attributed to the algorithm called word-to-vec, which essentially this is that was developed by Google, I think 4 years ago. And what the algorithm does, it takes all the words in the language based on a large corpus of text, and it does embedding of these words within a high-dimensional space in a way that words that are contextually related are getting very similar, getting embeddings that are very close to each other. And the reason for that, there are several reasons for that. Some of them are very specific to NLP, but other motivations to do that is that it facilitates a lot of very fast calculations. For example, in clustering application, you usually have to calculate an n by n quadratic distance matrix between the objects in your system, which is sometimes very, very heavy. But if you do this embedding, then it is fairly easy to find the close vectors to a given object and to do it faster. And word-to-vec captures well contextual relationship. And as probably those that are familiar with web attacks, you know that web attacks are not just pixels that are standalone and are not related to each other. If you see something, if you see SQL injection, then you are very likely to see another SQL injection. And you are very likely to see another SQL injection. So this idea of words and sentences well fits the web application security. The way word-to-vec works, it is based on a neural networks that does an optimization for this embedding. And there are several variants. Some of them are treat the order of the words, like something that is called a skipgram. The one that we use is called bag of words. It's independent of the order. So it doesn't care about whether I comes before love or love comes before I. It just treats them in the same way, which is, makes more sense in our arena. The success of word-to-vec in NLP attracted other domains who try to harness the same success to their world. And indeed, there are in the bioinformatics arena, there are algorithms like Gene2Vec that takes genetic sequences and that does their embedding within such a space. Gig2Vec, I heard in the Fiverr. Business2Vec, I heard just last week in data science conference in Jerusalem. And actually, there is this kind of a trend of anything to vec. And we said, why not? Why not having the malicious web traffic to vec, or in short, multi-vec, and join the party? So here is essentially the zoom out of the flow that we are, of the processing that we are doing. So we start with attack data points. Attack data points, they have different types. These types are represented here by colors. A spoiler, we're going in the, when we are going to show the embeddings, there will also be such a color coding. We aggregate the attacks into sessions in a way that Ori will elaborate on later on. And we then convert the sessions from the attack arena to the language arena. We convert them into sentences. And then we activate the word-to-vec algorithm to do the embedding. Now, the word-to-vec can generate vectors of different sizes. So we use 30 dimensions in order to give us and you the opportunity to see all these vectors together. We used an algorithm for dimensionality reduction, which is called TSNE, in order to throw them into a two-dimensional subspace, and the result is there.
Okay, so what we did exactly for this model? We started with the session aggregation, which means that we take malicious requests that came separately, and we aggregated those requests into a sentence. So a sentence or a session is not the same when we're talking about HTTP session. I'm going to explain exactly what do I mean by that. The reason we did it is to apply the word-to-vec algorithm, which is based on contextual information, the same as natural language, which is arranged by sentences composed of words. So our session or sentence is a list of requests which are grouped by the source IP, the source device, and the target site. And we also added a separation of a 15 minutes interval, meaning that if we did not see any request in that session for 15 minutes, then we split it into two separate sentences. So this is what we did with the single request and aggregated into a single sentence. So the next thing we had is we wanted to model the attacks, the vector of the attack, but we had the insight of the security rules that were triggered. So a malicious request is composed of the attack type, SQL injection or XSS, etc., and it has the malicious action, the exploit of the vulnerability or a payload. And Imperva's WAF detects the known exploits and payloads using a set of rules. So on the one hand, we have the malicious actor, and on the other hand, we have a web server with two types of SQL injection vulnerabilities. And the attacker creates malicious requests and sends them through the WAF, which then blocks these requests using the security rules. Later on, the attacker might create other payloads of requests to exploit the second vulnerability, and again, these requests are blocked by our WAF and triggers the security rules. So now that we have presented this in this concept, I want to talk about how the rules are being selected. So a malicious request might trigger more than one security rule. In this example, the SQL injection, we have 4 different rules that are triggered for the single request. And modeling the attack vector into a word means that we need to select which rules represent this request. So we can use the 2 options. One option is to use the rule set, meaning that we take everything, all the rules that were triggered for the single request, which is more accurate, but it has an exponential number of rule set words. It grows very large when you have long sentences and a very long attack. On the other hand, we chose to use one representative rule, selecting it by the severity, by how accurate the rule is, and how common it is. Meaning that we chose the least common rule to represent a single request. And of course, you have even more complex examples, such as this one, which incorporates 8 rules, 8 different rules with various types. And again, choosing the one representative is based on the parameters that I've explained earlier. So now that we have the concept of what is a word and what is a sentence, we grouped them together. We took the separate requests, chose a representative rule for each one, and combined them into a sentence, which is now the same as a natural language. We can feed it into the word-to-vec model. And let's see a demo of how it looks.
Okay, thank you, Ori. So what you can see here is the embedding of the rules. Actually, this is not all the rules of the WAF. It is just a significant amount, significant portion of them. There is the color coding, so the rules of the same type, of the same attack category, are having the same color. For example, you can see all this SQL injection cluster. And what you see in this text is actually in the left column, you see the metadata about the rule itself. What is its identifier, its type. And then you have the next 5 columns are the 5 nearest neighbors of this rule, and their similarity, their location. And the most important item here is these numbers, which represent the conditional probability, the mutual conditional probability between this rule and the neighbor, which means that, for example, whenever this rule was chosen to represent a malicious request, in 2/3 of the cases, in 2 out of 3 cases, we have seen this rule coming either immediately after or immediately before this rule, meaning they were captured within the same sentence. And for the other way around, it was almost 100%, 93%. Can you zoom out for a second? Okay, so you can see this SQL injection cluster. Can you point me to this one, Ori?
Which one?
No, the bottom one, yes.
Okay.
So these guys are, for example, file upload rules, which again, we can see them that they tend to come together. This is not very surprising. Actually, this is exactly the picture that we expected to see, because we know when someone wants to do file upload, then he tries different things, and these different things are being captured by different rules of the WAF. So we can see here numbers that are even more significant than that. Another example, let's take this one, Ori.
Which one?
This one. Okay, thank you. This is slightly different because what we see here is rules of different types, of different attack categories that are coming together, which is, at the beginning it was surprising, but then we looked at these rules and we see that one rule is a file upload, which means that the attacker tried to upload some malicious file for any purpose to the web server. And next we are seeing backdoor communication, meaning that someone is trying to communicate with a backdoor. So, but then we figured out that it makes a lot of sense, because the attacker, at the first moment, it tries to do the file upload, and if he succeeds, it then does backdoor communication. And then we wanted to go and let the customer know, because this is something that actually happened. It means that it has the file upload was successful and it has the backdoor installed. However, go back to your presentation. So some of our security experts provided an alternative explanation that and showed us this example and other examples. This is, I think, is called X-Attacker, which attacks a plugin called Cherry, where there is the attack script. What it does is first it tries to do the file upload, the upload of the backdoor, and immediately later, maybe even in order to validate that it was successful, he goes and tries to communicate with the backdoor. So what we've seen was not necessarily a successful file upload, but maybe an unsuccessful one.
Okay, so after modeling our War2Vec version, which we called Mal2Vec, we came up with a few applications. What can we do with it? The first application was to find false negatives, and by which I mean that we have some security rules which are in research mode, meaning that they are not blocking. Usually we use it to gather information and intel about what's going on over the network of our customers. Sometimes these rules are just regular rules in staging mode, which means that we want to move them to blocking, but we test them before. So using our version of War2Vec, we were able to identify such rules in research mode, which correlates highly with the other blocking rules, and which is suggested to us that we can use these research rules and maybe create a new blocking rule to capture the attacks that we are not currently protecting against. And I'm going to show you an example of such a rule. We added to this diagram one second. Okay, so this is the original one, and we added all the rules that are research mode. You can see that they are a little bit transparent, like this one and this one. So next to this cluster of SQL injection, we found a research mode, which has a very high correlation with all the others in that group. It is, when we did the testing, it was not blocking, but you can see that since it is highly correlated with other rules, firing together, this is a good candidate to move to blocking. Another example that I'm going to show you is this one, which is remote code execution rule, and again, very highly correlated with other rules. All of this information, based on many attacks and requests, is very visible thanks to the word-to-vec model and the TSNI dimensionality reduction, which is this diagram that you can see. So, an example, a concrete example of such rule is this one, which is the research rule is an attack against the Apache Strat vulnerability with over 900,000 hits in 3 months, and it highly correlated with the path traversal attack, over 700,000 hits in 3 months. And the dominant client used to launch these attacks was the white hat vulnerability scanner. And in our model, in the word-to-vec similarity, we got a 99.9% similar between these two rules. And so this was the main motivation that we came up with to begin with, what we wanted to achieve. Another application that I want to present here is scanner modeling. So we wanted to detect automatic tools which impersonate to be a browser. So how we did it? We created a separate Mal2Vec model for a common scanner, one model per scanner. We selected an attack sentence which has a browser as a user agent, Chrome or Mozilla or Firefox. And then we found the model which has the highest correlation with that sentence. And the result was the probability for each model to be the origin of that sentence or that attack. So this is a concrete example. You can see here that the user agent is Mozilla Chrome, and the sentence is composed of path traversal, file upload, an automatic attack, and remote code execution. On the left, you can see the rules numbers, and on the right, the types. And the diagram shows the probability that the model produced for each of these tools that we modeled. More examples are here. You can see the Nessus scanner, the SQL map, which not surprisingly based on the SQL injection attacks. And you can see on the other hand that you don't always get the most perfect prediction or correlation. Sometimes you have two set of scanners which correlates with high correlation to the attack. But it gives us better understanding about the origin, even though we ignore the declared web application or user agent.
Thank you, Ori. So we have several other applications that we had in mind that we found this modeling useful to assessment of the relation between different events. And when we are trying to understand, to reconstruct the narrative of the attacks, we see a lot of, I call this a security pixels, and we want to get security picture to understand which events are related to each other, they belong to the same attack. Then we use the fact that the events had triggered rules that are very close to each other as an indication that they are close. And if they are distant from each other, it is an indication that they are not related. In order to, even for assessment of the severity of the attacks, whenever we see a sentence that includes words that are distant from each other, then one possible explanation is that this is something that is unique, that is not standard. And think of that from a security officer perspective. Whenever someone does spray and pray and activates different scanners, then okay, this is yada yada, we are good, we know we are protected, everything is good. But whenever someone is doing something unique, maybe this is a personal attack, a targeted attack, someone is trying to attack specifically his application, and this is more concerning and maybe requires some action from their side. And also, it makes us very happy from a research perspective. We have this modeling for doing analysis of the attacks. We have a very nice and good picture of the attacks that we're seeing, the relations between them. And it is good lead generation for analysis of detection of unique things that are happening within our customers' ecosystem. So let me summarize. So first, I think we've seen that the web attacks fit very well this work-to-vec model. This was our basic assumption, and it was actually, we saw that this is correct. This idea of words and sentences and security events and sequences of web attacks that seem that these two words have a lot of in parallel. And it can be used for a variety of security applications. We found several ones. Maybe others can find the others, each one in his domain and what anyone with his interest. Conclusions. So first, AI technology is proven again as a game changer in security applications, in all, from whatever direction you look at the world of cybersecurity. AI can be used to improve it and to make things much better than before. Also from the attacker's perspective, but also from our perspective. And more important, when bringing security experts and data scientists and data all together in the same room, or in the same building, or the same world, then interesting things happen. Thank you very much. And
any questions?
Can you repeat the question? Can you repeat the question maybe from the mic so everyone hears?
Yeah, what are you using to run the models? Hadoop or another system?
Which implementation of Word2Vec?
Yeah. We just use the Python library, which is...
I think it is a Gensim.
Gensim,
right?
yeah. Any other questions?
Okay. So we are considering maybe to release this as an open source at some point. So stay tuned.
Yeah. Thank you.